Hello everyone, I'm from Nankai University. I'd like to present our recent work on dynamic binary translation. The title of our paper is DQEMU, a scalable emulator with retargetable DBT on distributed platforms. As we know, dynamic binary translation is a key enabling technology for many important applications, such as legacy code production translation, heterogeneous server consolidation, mobile plus IoT computation, offloading, and so on. However, the scalability of DBT is limited by computing resources inside one node. We did a pretty simple experiment using the training DBT QEMU, running parallel programs from Parset benchmark suite on an x64 dual-core machine. So ideally, the speedup goes up with the incrementation of threads. However, its saturate rate is around 2 because it is running out of computation resources. So our goal is to enable DBT to utilize compute resources across nodes. So a distributed DBT is such a system that can utilize multiple nodes' computation resources and serve one guest application. And there are several challenges when we design such a system. The first is how to maintain guest cache coherence. Note that the guest application do not know it is running on a distributed system, so we have to keep the cache coherence transparently. And the second is how to emulate guest system calls. A system call not only affects the guest memory region but also has a side effect to the host kernel. So how do we keep the consistency between different nodes in terms of host kernel state? And how to emulate guest atomic operations. In dynamic binary translation, we have to provide equivalent semantic between the atomic operations of RISC and sys. And how do we still keep it correct in a distributed system? Before we go deeper into DDBT, we first know how does DBT work. So DBT takes into a guest code and translates it into a simple, portable intermediate code. And the intermediate code is then optimized and translated into executable host code. Thus, the guest, and we call this procedure as tiny code generator (TCG). So DBT is a user process running on a host operating system that has multiple TCG threads in it, and each of them corresponds to one guest thread. There is a memory region dedicated to emulate the guest memory behavior. So a TCG thread first translates the guest code into executable host code and then execute the code to emulate the guest behavior. So a distributed DBT should look like there are multiple instances running on different nodes, and there is a distributed shared memory across nodes and maintain the guest memory region's cache coherence. We did not synchronize all the virtual space of the process to avoid extra overhead, but only the guest memory region. So to help them communicate with each other, we divide them into two groups. There is only one master node that has manager thread. Each manager thread corresponds to one communicator thread in a worker node. Note that master node itself is also a worker node. So to keep cache coherence, we have to pick granularity, synchronized granularity, and to check the cache blocks privilege. There is a straightforward solution, which is to implement a software-based instrumentation that we can check on every guest memory access. But this can introduce large overhead. So there is another choice, which is to use the hardware-based memory management unit to do the host page privilege check automatically. So we choose to use this solution with the page size granularity to do the cache coherence formula. And there are we can use distributed or centralized protocols. We first use MSI centralized protocol to see what's the performance of such system. MSI is a brief for modified, shared, and invalid. Those state corresponds to one page protection. And after we implement the distributed shared memory, we found that it still cannot correct emulate the guest behavior, since the system calls also affect the host kernel. For example, there is a guest system call file open in node 2, and if we emulate the file open in different nodes, it is open in different files, and this is not what we want. So system call not only affects the user space descriptor, but also affects kernel space resource manager. So system calls also affects host kernel. To keep the consistency of host kernel, we divide the system calls into two groups: global system call and local system call. The local system call has a negligible effect to host kernel, while the global syscall must be sent to master node to do the emulation in order to keep only one correct host kernel in master node. We have to send not only the Syscall parameters but also the guest CPU state to help master node correctly emulate the system call. As for the emulation of atomic operations, there is load link and store conditional in RISC and compare and swap in sys. When translating LL and SC into CAS, QEMU introduces potential ABA problem. To avoid such problem, we provide a ABA-aware mechanism to check ABA problems. The detail is described in paper. What we are focusing on is the cross-node emulation. So take lock as an example. We implemented a hierarchical lock. So if there are multiple threads inside one node that is emulating atomic operations, we obey the consistency model introduced by Armor, and when there are intra-node conditions, we still use the MSI coherence protocol since it is a sequential consistency. After we implement all of this, the system can finally correctly emulate the guest behavior, but it has serious performance issues. One of them is the force sharing. Force sharing refers to there are different CPUs trying to write to different locations inside one cache line. So the cache line is frequently invalid by the other CPU, so the cache line is ping pong among them. The probability of force sharing increases from 64 bytes to 4 kilobytes, and each cache miss costs originally 20 cycles, and it is increased to over 100,000 cycles when we have to fetch the page from network and return from page fault. So on the left side, the figure shows that the DBT translates guest memory address into host memory address. We want to utilize this to implement a mechanism called page splitting. So if there are different nodes trying to write to different locations inside one page, there is a force sharing. So after several times we we would create shadow pages and map each part of the full sharing page to the new created shadow pages, so that the shadow pages can maintain local at different nodes. Using this mechanism, it can reduce fault sharing possibility, not the cost, and it is compatible with cache coherence protocol, since the shadow pages is still host page, then still can be checked by host MMU. And we found that if there are data sharing among nodes, we can detect if there is a heavy data sharing between two threads among two nodes, and if so, we will move one thread to the same node to reduce the data sharing between nodes. To achieve this, we use a source code hint to generate a no-op for guest binary. It won't affect guest binary's behavior, but it means a call DQEMU schedule to dynamic binary translator. And we implement page forwarding to use the network bandwidth to cover the network latency. So we take a record on every page request at master node. If it is a sequential access, it will trigger the forwarder or prefetcher to forward the next 10 pages to the requester. And if it is still a sequential request, it will then forward the next 20 pages and so on. We are curious about the performance of the provided mechanisms, and we set up a cluster with 7 quad-core nodes. Each of them has a quad-core Intel x84 CPU, and the guest architecture is ARM. We take DQEMU 4 as our baseline. So we first measure the memory access performance. For the sequential memory access, DQEMU has a throughput of 173 megabytes per second. And what if we are accessing memory from the remote? We found that the throughput falls dramatically, and there is a 400 microsecond latency introduced by network. But if we turn the page forwarding on, the throughput goes up back again, and the latency has also been improved. As for the fault sharing, we created 32 threads to accessing different locations inside one page. So for the origin QEMU, it is running on a shared memory processor, and the coherence granularity is 64 bytes, so it won't suffer from fault sharing. But for DQEMU, the fault sharing of one page will lower the throughput to only 2000 megabytes per second. But if we turn the page splitting on, we found that the throughput is even better than our baseline QEMU. So this is because if the page splitting is turned on, each shadow page remain locally for every node. So every node is continuously accessing its own memory, and there are totally 4 worker nodes, so the throughput is almost 4x comparing to the QEMU. And this is exactly what we want, since we are using more computing resources and we gain a better performance. So what's the scalability of such system? We measure DQEMU with an ideal parallel program that has almost no data sharing among threads. We found that DQEMU has a nearly linear speedup when the slave node goes up. So how about the real-world applications? For those applications that have little data sharing among threads, DQEMU has a pretty good performance. So the blue line represents DQEMU speedup and the yellow line is the baseline, which is QEMU4. We can see that as the slave node goes up, DQEMU is continuously gaining speedup. And with the optimizations turned on, which is the page forwarding as the orange line, you can see that it enables DQEMU with a better scalability. And for the full optimization, like page splitting and page forwarding, you can see that when there are more than 4 nodes, page splitting is improving DQEMU's performance. For those programs that have heavy data sharing and data dependency among threads, DQEMU has a bad performance. For example, X264 is a media encoder with multi-threaded support. If we run the origin DQEMU with more slave nodes, it is taking the longer time, which means DQEMU cannot utilize more resources to gain a speed up. So to solve this, we first turned on all the optimizations, and we analyzed the source code data dependency and did some loop unrolling and insert some proper hints to help DQEMU schedule the guest threads among nodes. And finally, with those optimization support, DQEMU can use multiple nodes compute resources to gain a speed up when there is more and more slave nodes. And there are still some questions left for us. So should we design a more scalable coherence protocol, such as distributed coherence protocol, since that the centralized coherence protocol may have scalability issue when there are a lot of slave nodes, and random memory access hurts DSM's performance. So can we design something that can help reduce the latency of random memory access? And what kind of program suits DQEMU? I mean, those programs that have data dependency and data sharing wouldn't have a good performance on such DSM. So how to recognize those programs to avoid such problems running on DQEMU? And shall we support various host ISA so that it could become a heterogeneous cluster that can run one guest application? Yeah, thank you.